geometry and proof. They go hand in hand. Got to find these proofs, got to find some facts about shapes. That's what we're doing this year. And hey, we're getting some new shapes that we're going to be able to prove some things about. And you guessed it, it's about triangles. So reminder, the name of this chapter is called Congruent Triangles. And of course, that's what we spend the bulk of our time doing is determining the ways we can kind of quickly establish one triangle as congruent to another triangle. We've got the SSS method, SAS method, ASA, AAS, which is a theorem postulate, and the HL method, which is also a theorem postulate. Okay, so now you have those, and we're going to use that stuff to determine other things about other shapes. We're going to continue that in Chapter 4, even in Chapter 5, right? We're going to be applying what we know about triangles to learn things about other shapes of different sizes and different permutations and whatnot here. So one thing in this section is we're going to do more about proofs and proving things, getting new facts about specifically triangles, okay? So specifically in triangles, we're talking today, we're going to have something called a median we're going to talk about a little bit. You have a median featured right here, median featured right there, median featured right there of triangle ABC. Has 3 medians. We'll talk about that in a little bit here. We also have altitudes, okay, altitudes. So there'll be a name of a shape that we'll get. Definition, I'll talk about it. We'll have to do it with the problem set. We'll have to use this year. What is an altitude of a triangle, right? Well, a mountain, right? A mountain has altitude to it. What does an altitude mean in terms of a mountain, right? Look, triangle ABC kind of looks like a mountain. Kind of looks like a mountain, right? Kind of looks like a mountain. What are the altitudes of a triangle, and what can we prove about those altitudes, right? We want to get to that a little bit later on this year. And then finally, we're going to talk about perpendicular bisectors. So that's another thing too, where in triangles are going to have 3 perpendicular bisectors, and we'll talk about what those shapes mean. And perpendicular bisectors aren't just for triangles. They're also for any segment. Any segment has one and only one perpendicular bisector. So you're going to learn about what those 3 things are today. And yes, there are going to be theorems at the end. 4 theorems that I hope to cover. And this is going to be kind of a long lecture, I'm thinking, but it's basically an introduction. I'm going to go through this section with you, introduce it all, and then for your exit ticket, you're going to have a lot of the classroom exercises, okay? So just sit back, take some notes, write down what all 3 of these things are, try to make some observations over the next hour or however long this takes, and then that should hopefully make the classroom exercises, the exit ticket, flow a little bit, because you've heard stuff, you've experienced stuff, along with good old Mr. Fortin right now here. All right, we got section 3.6, medians, altitudes, perpendicular bisector. So let's get into it. We're going to structure it with what the definitions are, and hopefully point some things out to you. I'll be like making observations as we go along through. Unfortunately, we can't really have a back and forth this year, right? Discussion like we would normally do in a normal year. So you're just going to have to hopefully be taking notes down. Hopefully, maybe as I've blabbered on already, you've written down the definition of a median here. This is all from the textbook, so maybe you want to pre-read the textbook. I don't know. You're your best teacher, right? I'm one of your teachers, but you're your best teacher, so you got to decide what's going to help you learn this material here. So all from the textbook. We'll go through everything in this section. I'm just gonna go through the section that you're probably reading on your own and say a little bit more about it now. Okay, so let's dive on into it. All right, so a median. The first thing we need to know about triangles today is that there's a particular shape that we're going to study this year that has some interesting geometric features to it. And this will come up later in the book as well too here, but a median, that's a median. So here's a definition, right? We have a definition. This is definition of median. Okay, so if we have a median, then what can we say? Well, that'll be a theorem coming up later. But anyways, a median of a triangle is a segment, the segment that you can draw, right? Because through 2 points make a line. But anyways, is the segment from a vertex here, okay? So this is the median from vertex A, okay, median from vertex A in this triangle right here. So it's the median is the vertex to the midpoint of the opposite side here. So that means side BC, right? Side BC right here would be opposite the angle A, right? Opposite the angle A here. So what I got for my median is this right here. So I would just sketch this out real quick, right? Because here's your first glimpse of what a median is, okay? It creates 2 congruent segments out of the opposite side right here. So if I wanted to redraw a different diagram real quick, just to show you that every triangle has a few of these medians here, this kind of looks like a right triangle right here. But a median, right, would be like this guy here. Like, oh, midpoint's probably around there. midpoint to vertex, okay? Midpoint to vertex. So maybe you just write that down shorthand. What a median is midpoint to vertex, or vertex to midpoint. Vertex to midpoint right here. Here's our a median, okay? Median, right? Middle, median, right? Like median, right? Think about the data, right? If you have a data set, you can have a median value. That's the middle value, right? Median goes from midpoint to vertex. That's your first feature that you're going to learn today. And each triangle has 3 medians, right? It has 3 medians, because here we would have our median from vertex B, from vertex B, and that's going to be right here. Boom, okay? Vertex to midpoint, vertex to midpoint, vertex to midpoint. That's how you can remember that. I would write that down, vertex to midpoint. Okay, there's a median. And then finally, we have from vertex C, boom, to the midpoint of segment AB, right? Because angle C, what's going to be opposite angle C in triangle ABC is segment AB, right? AB doesn't include C. So we have C and then AB here, okay? So we have these so what we know, right, if given to us, we have a median, then, right, if given to us, we have a median drawn from C, then we're going to know that that median here, say that this is point Z right here, we can use the definition of a median. Sure, you can use that in a proof. If we get CZ is the median, right, CZ is a median of triangle ABC, then we can say that AZ must equal ZB, okay? That's how we can use that in a proof. You are a median if and only if you are drawn from one vertex, if you originate from a vertex and you end at the midpoint of the opposite side. So you'd have to create 2 congruent segments out of there here. So definition midpoint, I knew if I have a median from vertex B, then I would know that AX would have to equal XZ, right? XC here, because I would know that that's a midpoint by definition of median. Okay, so that's sort of how medians get used here. And there'll be some interesting, when you have, so just a little preview here, when you have all 3 of the medians drawn in here, because remember, this is one median, but we already talked about BX right here. That was another median, so I'm going to the midpoint right here. And look at this, I'm going to draw, let's make this Y, I guess. Let's draw a Y to the midpoint here. Oh, interesting. Okay, that's a median, that's a median, that's a median. And look, they meet at one single point. Those 3 lines intersect in a single point here. So there's no transversal there. It's just like none of these 3 lines would be counted as transversal, the other 2. They meet at one specific point here. There's something called concurrence. That's a point of concurrency right there. Interesting about medians. That might come up a little bit later, and there could be some different things with the distances from the point of concurrency to the sides and whatnot here. Just more information, right? More connections, more math formulas, and stuff we know about the world that we're going to establish and prove later on this year. All right, next up we have altitude, okay? So we have medians, we talked about them there. We're going to move on to altitudes right here. An altitude of a triangle is the perpendicular segments from a vertex to the line that contains the opposite side. Okay, it's kind of a mouthful. The 3 altitudes of acute triangle ABC are shown below. Okay, so let's check it out here. We got another definition for you. Definition of an altitude, okay? Definition of altitudes here. Okay, it's the perpendicular segment. So here, right, altitude, okay, is vertex perpendicular to opposite side. Okay, you write that down. That helps you remember exactly what an altitude is. Okay, definition of altitude is from the vertex, the segment from vertex perpendicular to the opposite side. Put that in your notes. Have that stored away, right? Median, vertex to midpoint. Altitude, vertex, that's the segment that's perpendicular to the opposite side from the vertex, or from the vertex here, okay? So here we have an altitude right here. Vertex A, this is be called the altitude from vertex A, okay, would be, well, I need to draw it in such a way. If I drew it right here, this would be acute this way, and this would be obtuse right there. I wouldn't have that. If I drew it like this, like it looks like it would be obtuse over here, and it'd be acute over here. So there's only one way. Through a point outside of a line, to a line itself, there's exactly one perpendicular that can be drawn. And then if that's from a vertex to, and the other line, the vertex is the point, and the other line is the line segment that's the side of a triangle here, that would be an altitude, okay, an altitude. So there'll be definitely things we're going to prove related to altitudes right here, okay? One thing, hey, check this one out. Picture that this is a mountain. Pretend that this is a mountain, right? We're on top of the mountain. Like, you ever go skiing? People ever go skiing or snowboarding, right? We're on top of the mountain, right? We're at Squaw, right? What else is there? Heavenly, right? Heavenly, oh, yeah. There we go. A little snow up top. There we go, snow up top. A mountain has altitude, right? Altitude. What's your altitude right now? What's your altitude? Do you count the altitude as like the distance you are from the bottom, like over here? Is that the altitude right now? No, that's not the altitude. Altitude's vertical height, right? Vertical height here. So this would be the altitude, would be the perpendicular to the ground, right? Perpendicular to the ground. So vertex, again, perpendicular to the opposite side segment right here. This would be the altitude, okay? So this comes as a geometric term that we use to express, right, how high we are from the ground, right? Above a vertical line to the ground. Draw a vertical line to the ground, that's your altitude. I'm on the second floor right now of my new home here. And how high I am, I'm not gonna count like when I go down the stairs and I come around. I'm gonna if I have to drop a perpendicular down to the surface of the earth. And that distance would be the altitude here, okay? So here's our altitude. Altitude right here, vertex to the other opposite side perpendicular, and here is the final altitude here, vertex to opposite side perpendicular. This would be the altitude from C, okay? Maybe we'll call that CZ right there. CZ right there would be altitude. So if given to you that CZ is an altitude, then you would be able to deduce by definition of altitude that CZ is perpendicular to segment AB. Right, segment AB here. Here, if this is BY, I would be able to deduce that BY is perpendicular to AC, okay? And notice here, if I did all three of them, let's make this one X right here. If I drew AX, which is about right here, okay, these are all the same triangle, note this here. If I drew all three of my altitudes, what do we notice about this here? Drop it straight down. What does it also have? Look at that. They intersect in exactly one point. They have a point of concurrency right there. So we're going to notice things, again, about distances and about different ways that the reason why they all converge there and how you can actually prove that they're going to intersect exactly one point. It's possible to do that there. All right. Anyways, another quick question that they have here is, this is sort of a difference here. Medians are always going to be inside the triangle. You draw from a vertex, right? So even if it's like, I'm sort of getting ahead of ourselves here. If I have a big obtuse triangle right here, okay, my medians are always going to be in the middle of the triangle because, again, I'm going to a midpoint here that's inside the triangle. So I'm traveling inside the triangle for my medians. Okay? My medians are always on the inside here. They asked about this. Do you think that the altitudes of a triangle are always inside of a triangle? Okay? Well, if we look at this one here, oh, the perpendicular, right? Perpendicular would be inside the triangle right there. But what about this? How would I draw a vertex from this, an altitude from this vertex to this side, for instance? So here's where we need to read, because we can't actually draw a perpendicular to over. The perpendicular to this side kind of would be over here. The side would have to be over here. So this is where in the definition we need to be a little bit more careful reading this about the altitude here. An altitude of a triangle is defined as the perpendicular segment from a vertex to the line that contains the opposite side here, okay? So if this were line BA, segment BA, I would need to extend this line to figure out that my altitude is over here, okay? So here's the second altitude. So there's an altitude here, there's another altitude here. Interestingly enough, you'll see later they actually would intersect outside the triangle, like down here, and the final altitude would be, yeah, like right here as well. All right, anyways, we're getting kind of messy here, so let's maybe look at this diagram right here because they're trying to show you this a little bit differently. This is triangle, here's a triangle right here. We're still talking altitudes right now. We haven't gotten to perpendicular bisectors. So this is triangle LKN right here. And notice it's here, and it's here, okay? it has 3 altitudes. Any triangle has 3 altitudes, and these will be things we study this year. We're just introducing them today. 2 of the altitudes of a right triangle are also legs of the triangle. Anyways, I'll get to that in a second. But 2 of the altitudes of an obtuse triangle are outside of the triangle, okay? So your altitudes are kind of weird. A lot of people are just like, well, where's the altitude? How do I draw them? It takes some practice to do that, okay? So here, remember, what is an altitude, right? An altitude is vertex, okay, is a segment from vertex perpendicular to opposite sides line. Okay, opposite sides line. So wordy, right? Wordy. And I know a lot of people don't like writing down a lot, but I gotta say that's the thing that I see correlated most with how good of a student you are, right? With grades you get is the people who write more do better, right? Do better on quizzes and tests and work through things. So anyways, I encourage you to write down every definition. As wordy as they are, write down the whole thing if you can. If not, right, I know a lot of you guys don't like to write down. You can write down a little bit here, but like just know you probably won't get it as well as if you just wrote the whole thing down, because then you'll pick up, if you read the whole thing down, you'll pick up on things you wouldn't have noticed if you were just reading it here. So anyways, if we get back to this here, we have an obtuse triangle, 1, 2, and 3. If I'm gonna draw my 3 altitudes in here, boom, okay, vertex to the line containing the opposite side here, well, that's actually gonna hit the opposite side. It's actually gonna do it here. There's only one perpendicular that I can draw through a point K to line LN, and that's it. That's my altitude right here. Here, from the altitude from, so the altitude from vertex L, right, would have to go to line KN, not actually the side KN, the line KN. So the line containing the segment KN here. So they gave it another point. You can call it line HN if you want to. But the idea of this is that if I'm at this vertex right here, I can't, like, it's going to be obtuse going on this direction here. And it's going to be acute going on this direction here. See, if I draw that, that's not an altitude because it's not perpendicular, right? It's acute here, it's obtuse there, not that. So there's right through a point outside of a line, there's exactly one perpendicular that can be drawn. So we are not constrained to being within the actual triangle here, okay? So here is our altitude in this one. I would sketch out the obtuse, just sketch it real quick. Sketch all 3 of these examples, or sketch one obtuse triangle like that and sketch all 3 altitudes, and you'll see actually, we'll see in a second, they're all gonna hit each other in the same place here, okay? So we have an altitude here that's outside of the triangle because we needed to extend, right? We needed to extend this line, right? Because this is line KN, and there's only one perpendicular we could draw to line KN through point L, right? And it happens to be outside the actual triangle itself, right? The triangle itself here, okay? So this here, right? This here is the altitude from vertex L to line KN. Okay, final altitude right here from point N. Well, if we're going from point N, we got to be looking at the other 2 angles here. We got to, okay, there's our segment right there. So N, opposite sides, LK. So the line containing the opposite side here, right? We're not going to draw our altitudes over here. We got to extend that line and figure out where that's going to be perpendicular, and that's over here. Okay, so here's our final altitude. Okay, this is altitude from vertex N to LK. Okay, to LK. All right, so there we have it. That's perpendicular. There's our 3 altitudes. Check it out here. I might actually show this to you real quick because it's kind of neat. If I extended this here, I'll extend this a bit here. If I drew remember this is where my altitude was from point L. If I drew that, boom, I hit down there, okay, interestingly enough there. And if I draw this altitude, I hit over here, okay, I hit over here, right? This is the one that's over here. So now I have 1 altitude drawn. I have the second one kind of eyeballed and moved that from over there. Third one here from point K right here. But if I extend that in this direction, interesting. We hit in one particular point right there, okay? This is something called, it's not defined in this section, but this is something called a point of concurrency, and is something to keep in mind. So we'll study these points of concurrency later on this year because any triangle, if we extend these special lines, we actually will meet in one place, and this is a defined center of the triangle. Believe it or not, this is called a center triangle, something called an orthocenter, even though it's not within the interior of the triangle. Orthocenter. What is this one called here? This one's called is this the centroid? Yeah, this is the centroid right here. Centroid right there, centroid. Anyways, getting ahead of myself, saying some fancy language we have earlier here. All right, next one here we have perpendicular bisector. All right, perpendicular bisector of a segment is a line or a ray or a segment that is perpendicular to the segment at its midpoint. In the figure at right, line L is a perpendicular bisector of segment JK. In a given plane, there's exactly one. I'm just reading this here. Why am I reading this here? I should talk about perpendicular bisectors for you guys real quick. All right, so perpendicular bisectors. A perpendicular bisector of a segment is a line. It could also be a ray or a segment. Basically, it's a line though, or the subset of line. But anyways, line that's perpendicular to segment at its midpoint. Okay, so we've been talking about this in terms of triangles so far here because a triangle does have 3 medians. It has 3 altitudes. It also has 3 perpendicular bisectors, but a perpendicular bisector is defined for of a segment, okay? So you should probably say perpendicular bisector of a segment. What does it do? It intersects the segments at its midpoint and it's perpendicular, right? And it's perpendicular, okay? So any segment, I would have a little sketch of this here too. They already did this here. It's confusing when they already have their sketches on here, which is why we need to do it on a chalkboard, we need to kind of do it in a video like this here too. If I have a segment, we'll call this XY right here, okay? 2 points, through any 2 points, I can draw a line segment, right? 32 points, there is one line, so I'll include the segment that just connects those two. We have endpoints here. Any line segment has exactly one line that's a perpendicular bisector, okay? So what that would mean is if we find, let's see here, how many do we go over? 1, 2, 3, 4, 5, 6, 7. So about 3.5 and then 1 down. So this is the midpoint here, okay? So of course, with any segment's gonna have a midpoint, okay? And then through this point, I can only draw one perpendicular in this plane, right? The plane that is the actual sheet of paper here. And this in green, I'll do the perpendicular bisector. So I'm going to do it perpendicularly and here. And there are going to be some interesting connections we'll go through in a second about this thing right here. Okay, so this is a perpendicular bisector of segment XY. Okay, segment XY. Okay, let's give it a name here. Maybe I'll call this AB. Okay, so AB, segment AB. I would maybe just sketch this down, just get used to it here. Not segment, line, right? Line AB is the perpendicular bisector of segment XY. Okay, I could have also said that the way that they've written this definition here, I could say there's the ray. So you could say ray BA is a perpendicular bisector of segment XY. You could say that segment AB is a perpendicular bisector of segment XY, and that's fine. We'll be able to prove stuff about this stuff right away, actually. We're going to go into one theorem about this in a second, okay? Where have you seen this before? You might be thinking about where have I seen this before? Well, I've seen this before with isosceles triangles. Remember, with isosceles triangles, if I got an isosceles triangle right here, which is a common kind of triangle to have in designs, is we have this, we have this, we have this, okay? Oops. The perpendicular bisector, right, of like this segment right here. This is segments, we'll do the same thing too. We'll do XY. Its perpendicular bisector would go through the vertex of the isosceles triangle, okay? So remember, an angle bisector, right, angle bisector of the vertex hits the base of an isosceles triangle here. Let's make these be the congruent sides. The base of an isosceles triangle at its midpoint and perpendicular to it, okay, perpendicular to it. So a triangle has a perpendicular bisector like this. Let me draw the other two real quick here. So this is isosceles, it's not equilateral here. So here I need to find the midpoint and then maybe draw it perpendicular here, boom. Okay, so see I actually missed that vertex right there because this isn't an equilateral triangle. Okay, let me find the midpoint right here and maybe draw it perpendicular here. Maybe just sketch it out. And look at that. We meet in the same spot, right? Same spot right here, okay? Same spot right here. And it so happens in this example, it's inside the circle. But anyways, This is another point of concurrency, right? Another point of concurrency. So that's kind of an interesting connection here. It's kind of why they're lumping these together. We're studying a lot with triangles in this chapter, and medians, altitudes, and perpendicular bisectors of the sides of the triangles. There are three of them, right? Three of them, because there are three sides of a triangle, right? Three vertices. And they always meet in a single point, the same types, right? So the three perpendicular bisectors of the three sides of a triangle, they meet, they're concurrent in a single point. And this is something called the circumcenter of a triangle, okay? It's another center of a triangle here. And there's some like physics connections and like other stuff you can do with circumcenters and centroids specifically, actually, which is the median's point of concurrency. Anyways, you don't need to worry about that. You need to worry about this section, reading it and kind of hopefully getting it here. Okay, I think I've said exactly everything that they've said there. Let me say more here. Okay, so we need to get into some theorems here. I think we're doing okay on time. I apologize that it's so... it's not too bad, 25 minutes. We've had worse. There's a lot of information in this section. So let's at least go into the theorems. Hopefully I can introduce them today. And then again, on Monday, you're gonna have a second day of section 3.6, and that's when you're gonna get your problem set. So hopefully enough of this is gonna make sense. And this is really stuff we'll study more next semester and whatnot. So anyways, here's your first theorem though, okay? So we have a theorem. All right. And this is it. We don't use the numbers here. We just use theorem. So write this one out. Write this one out in your notebooks here. If a point lies on the perpendicular bisector of a segment, then the point is equidistant from the endpoints of a segment. Okay, write it out. Take 15 seconds to write it out and see what questions you have. 15 seconds. Ready, set, go. Forget about this diagram right here. You're writing it out. Write out the theorem. It's always important to write out the theorems, then you can think about it. You notice you won't miss anything, right? You look closely at it. You don't look a ton of detail, but ideas will hopefully come to you as you're writing that out. And perhaps it's like, well, what does equidistant mean? We should talk about that. But anyways, for this one here, we'll talk about this one, the logic around this one, with naming it out like they named out here. I'll ignore this diagram because I think this diagram is confusing here, but this theorem has to do when you have a perpendicular bisector. That means you have to have a segment. That's the thing that gets perpendicularly bisected, right? Is segments, okay? We have segment BC, okay? And if a point lies on the perpendicular bisector of a segment, so maybe I'll draw in the perpendicular bisector of segment BC. Okay, so sketch that out. Draw this out, right? Segment BC, draw the perpendicular bisector of it. Okay. I didn't really draw that super well. It doesn't really look like a 90-degree angle. This is where constructions, right? You're going to construct things. Or normally we would construct things, and normally we'd actually construct. We'd be able to prove that we've drawn a 90-degree angle. But here I'm just eyeballing it. Okay, 90-degree angle at its midpoint. Right, here we have point M, okay? They called it point X right here, so maybe I should call it point X. And the perpendicular bisector of BC, and they're gonna call this A. Okay, so then a point, okay? So this is the, given here, this is the perpendicular bisector. So maybe I'll write that one down, okay? This is the perp bisector. So it's given to us that this line AX is the perpendicular bisector here of segment BC. And the thing about this proof is if a point lies on the perpendicular bisector, so it could be anywhere, okay? It could be on top, could be below, right? This whole thing is the perpendicular bisector, right? All of these points on here, all these points in here are gonna fit this theorem in a second. So check this out. I'm gonna choose point X to be right here, okay? Point A to be right here. Okay, so this is a point on the perpendicular bisector, okay? And then we're going to get to some of the logic that we've been studying, working on recently here in a second here. If we have a point on the perpendicular bisector, it's given to us that BX is equal to XC because that's part of the definition of perpendicular bisector. It's given to us that this is a right angle, and that's a right angle because, again, perpendicular bisector is perpendicular to the actual segment. So we know that those are going to be congruent. Here, what it says here, if a point lies on the perpendicular bisector of a segment, then the point is equidistant from the endpoints of the segment. So maybe we should talk about this word equidistant, okay? Because this is a word that isn't really defined for you in the textbook, but it's maybe the first time you're seeing it, okay? Equidistant, okay? What do you think equidistant means, okay? This point A, is equidistant from the endpoints of the segment, okay? So if we're going from point A, right, if we're on the perpendicular bisector, here's what all this theorem really just says, is that this point from here to B, right, A to B, is equidistant from A to C. What do you think equidistant means? It just means equal distance. Equal distances away, right? Equal distance away. If you're equidistant from something, it means you're an equal distances away, okay? So for me, I got Lowell High School about 2 miles that way. I got the Golden Gate Bridge about 2 miles that way. I am equidistant to Lowell High School as I am to Golden Gate Bridge, right? If I do a run to Lowell High School and I run back, that's just as far as if I run to the bridge and then I come back, okay? So I am on the perpendicular bisector of the segment connecting the Golden Gate Bridge and Lowell High School. That's what that tells me, right? That's what it tells me. Anyways, equal distance away. So quickly just think to yourself for a second, what are 2 things that you are an equal distance away from? Equidistant away from, okay? One thing that maybe you can think of is we're probably like an equal distances away from what? Like Bismarck, Idaho, and El Paso. Maybe not El Paso. That'd be too far away. But right, even though a midpoint, right? Midpoint of the segment would be on the. This is why I thought it's an example. A midpoint on the perpendicular bisector, of course, is the same distance from B as it is to C. Okay, but the reason why this is an important theorem is that anything else on the perpendicular bisector is also going to be the same distance from that point to the endpoints here. So picture 3 cities, right? Picture 3 cities that kind of form like a triangle like that. It's possible, look at this is an isosceles triangle here, okay? So talking about the logic of this theorem a little bit here, the reason why we know, okay, so if we're trying to prove this as a theorem, look at this here, we're trying to prove, is AB equal to BC, right? This means equidistant, okay? This is equidistant, okay? If AB is equal to AC, then A is an equal distance away from B and C here. So that's what we're trying to prove. We're trying to prove, is AB the same distance as AC, okay? And how will we prove that? Let's look at the diagram here. Well, we're given that it's a perpendicular bisector, okay? So we could slow it down and kind of prove it out together here. So okay, so given to us that, all right, this is line L. Well, I'm going to call it line AX. Okay, so AX is bisector of BC, okay? You guys aren't fast forwarding, are you? 2, so that would be able to deduce that BX would have to equal XC, okay? Because a perpendicular bisector intersects the segment at its midpoint, okay? It's also perpendicular to it, but at its midpoint, and that is just definition of perpendicular bisector. Okay, so this is kind of a neat little proof here. We get that. We also know that AX is perpendicular to BC, and that is definition of perpendicular bisector as well. Okay, so it tells us 2 things, definition of perpendicular bisector. It tells us 2 things, right? It creates equal segments, and it is perpendicular, right, to the segment, to the original segment here. Okay, so now I can also say that angle BXA is congruent to angle CXA. Why do I know that? Well, it's perpendicular here. So perpendicular angles, so perpendicular lines form congruent adjacent angles, okay? Or adjacent angles formed by perpendicular lines are congruent to one another. It goes all the way back to chapter 1 right here. We get that. So we get these 2 angles congruent. So here we have a side here, an angle here, congruent to an angle here, and look, we have a triangle over here. We have a triangle over here. How many of those 2 triangles congruent? Do they overlap at all? Well, they kind of do. They share a side with one another here. Check it out here. AX equals AX, right? Distance AX, same as distance AX. Segment AX is congruent to segment AX here. So we have a segment in this triangle here congruent to a segment in this triangle. And the segments over here that were created by the perpendicular bisector, of course, is the midpoints of this segment here. We have two congruent triangles next to one another. SAS and SAS, right? Because of what we said previously about the perpendicular lines forming congruent adjacent angles here. So I got to say that reflexive part. So I got to say AX equals AX, and that's by reflexive. And we're going to get to our goal very soon, which is, again, showing that that point A, which is on the perpendicular bisector, same distance to B as it is to C right here, okay? So because I can get this triangle BXA congruent to triangle CXA by the SAS congruency postulate. And then statement 7, AB equal to AC, and we've solved what we wanted to prove by CPCTC. Again, these are corresponding parts of congruent triangles. So we know they're congruent. We can cross out those question marks here and arrive to our answer here. And that's what it is, right? That's what it's all about. If I know that AB equals AC, right? Notice here, A is a point, an endpoint in these kind of distances here. If AB equals AC, then here, this is the definition of equidistant, right? Then A is equidistant from B and C, right? From B and C. So to be equidistant from 2 points or 2 things, right, you need to have the same distance to both of them. So if A is equidistant from B and C if and only if AB equals AC, and that's what we proved there, okay? So, and we could have done this really anywhere on the perpendicular bisector, okay? So for instance, we could have chosen point A down there. Is point A in the perpendicular bisector? Yeah, it is. So it's the same distance from point B as it would be from point C, okay? And the same logic holds. The same proof of this theorem would actually hold here, right? Because, right, if we wanted to prove these are congruent here, right? It's on the perpendicular bisector. Hey, we have that. That goes to the midpoint of the segment. It's perpendicular here. It's perpendicular there. So those angles are congruent. Reflexive property, boom, SAS, okay? So we got ourselves a theorem right now. Anywhere on this perpendicular bisector, same distance from B and C. And that's going to be an important application coming on a little bit later, okay? One more about perpendicular bisectors that we have here. Let's check this one out. Write it down, write it down, write it down. You might notice some things that you're not sure about, that you need to pay attention to. And also, we'll create a new diagram for this one, because again, this is kind of confusing here. All right, if a point on is equidistant from the endpoints of a segment, then the point lies in the perpendicular bisector of the segment, okay? So this sort of gets us down to a little bit about what I was talking about earlier in terms of thinking about distance. If a point is equidistant from the endpoints of a segment. So picture yourself here, right? Picture yourself here. You're in city M for me, that's where I am. Memphis, I don't know. Picture yourself, you're in a city and you're like, you know what? We're about the same distance from Santa Rosa as we are from San Jose, right? Santa Rosa is right here. It takes you like 80 minutes to get to Santa Rosa. There's Santa Rosa for right here. And then here's J, okay? Takes you about, 80 minutes to get down to San Jose. Are Santa Rosa, San Francisco, San Jose, are they perfectly in a straight line? No, not exactly, okay? But M is equidistant from R and J. Let's just pretend this is a perfect scenario. You're in a city. You're the same distance away from 2 other cities here. What do we know, okay? If a point is equidistant, so if it's given to you, if you know you're the same distance away from one point as you are from another, right? This information is given to you. You can actually prove that that point M right there would be on the perpendicular bisector of the segment connecting those 2 other cities here. So this is just a helpful thing for design, a helpful thing for locating specific things and different attributes that we might be concerned about here, we might be concerned about in the future. But here, if I know that a point is the same distance from the endpoints of 2 different segments right here, this is given to me, I can prove this. I can prove that if I have that this perpendicular bisector is going to pass through that point. It's going to be on the perpendicular bisector right here, okay? So how do I prove this? Let's maybe get rid of this here real quick, okay? How do I prove this? Well, if you're a city here, city M, right? There's me in San Francisco, and you're the same distance away from these 2 other cities here. What kind of a shape would that make? You connect all 3 cities, right? Connect all 3 cities. What is the most specific name we can give to this shape here? What is this? Well, it's a triangle. What's more specific than that? Name that. It's an isosceles triangle, okay? And what do we know about the isosceles triangle, okay? In an isosceles triangle, okay, well, what we do to prove this is we can drop in an auxiliary set. We can drop in the angle bisector of the vertex angle, boom, boom, right? Through protractor postulate, we could take that angle RMJ, divide it in half, drop in that bisector right there. The angle bisector, right, would have to go through you because you're equidistant from those two other points. So you're part of the vertex of this isosceles triangle. The angle bisector of the vertex angle is, what does it do? What does it do to here? So RJ is the base right here. It is perpendicular to the base at its midpoint, okay? In other words, the angle bisector of an isosceles triangle is the perpendicular bisector of the third side, the base side of that here too. And that's what's gonna get you that proof right there, okay? Angle bisector of the vertex angle is perpendicular to the base at its midpoint. And that, right, would be enough. That would fit our definition of perpendicular bisector. Now that we've defined it in the book here, we can just say that the angle bisector of the vertex angle of an isosceles triangle is the perpendicular bisector of the base segment that you have there, okay? So, right, you could have done this anyhow, right? Like if I happen to know that this point here was the same distance here as it was to here, okay, as it was to here, it's very easy to prove that, because this forms an isosceles triangle. It's very easy to prove that this point here, this point X, is on the perpendicular bisector, which I have in green here, right? Which I have in green here. This is the perp bisector, okay? So you might be wondering, hey, these are pretty similar theorems. Yes, they are. Maybe think about them for a second. They're very similar. They are converses of one another, right? Here, they're just opposites here. So here, if a point lies on the perpendicular bisector, we're going to know it's the same distance, equidistant. That's what equidistant means. Equal distances away from the endpoints of a segment. If we know we had a point that's equal distances away from the endpoints of a segment, we'll know it's on that perpendicular bisector, okay? Usually this helps out with constructions. We should do constructions in second semester, and these facts here really help with those. I don't know if we'll do constructions this year. Okay, we need to wrap this up. We have 2 theorems left. Guys, these are the last 2 theorems of the entire semester. So I know this video has been long already. I know we've talked about a lot here. Let's think about it. We've talked about medians. Do you know what a median is? Do you know what an altitude is? Do you know what a perpendicular bisector is? Do you know how they all converge, right? There are 3 of them in each triangle, 3 of each of those 3 things. So 9 things total, right, that you could draw in a triangle like that. Each of the 3 things intersects at one single point. There'll be some other geometric connections we'll make from them. So what's a median? What's an altitude? What's a perpendicular bisector? Could you define those? Maybe think about those for a second. Okay, we're going to wrap this up, though. We're not going to really have a lecture on Monday. That's nice. You don't have to watch one of these videos here, because I just want you to see all the theorems today, this weekend, right? Just get it done with, do your exit ticket. 2 more theorems left the entire semester. Let's just get it done right now here, guys, okay? So before we go into these last two theorems here, there is an important definition, okay? So let me highlight this right down here real quick. This is an important definition, okay? Important definition here. And the definition is for the definition of distance from a point to a line, okay? For definition of distance from a point to a line. So here we have this diagram right here, but maybe ignoring this diagram here, let me just draw this out, because you can actually, between any point, let this be point R right here, okay, between any point and any line. So I'll draw in maybe line AB right here, okay? This is A, this is B right here, okay? There is one and only one distance here between this point and that line, okay? If we were to say, I'm here, right? This is where I'm here. How far will I be to the wall, right? To the wall here. We are not going to measure the distance from R to A, right? We're not going to do that. That's not the distance, right? If we have to think about distance from a point to a line, we're not thinking about the distance from R to B, right? That's pretty far to the wall. How would you walk to the wall? In what geometric manner would you walk to the wall here, okay? Well, if you've read the definition already, and I hope you have, it would be this. This here, boom, the perpendicular segments, okay? The perpendicular segments is the distance from a point to a line, or a line segments, right? Line segment or a line here, okay? So distance from a point to a line is defined as the perpendicular distance, or perpendicular, the length of the perpendicular. Let me read this down. So I write down exactly what I'm writing down here. The length of the perpendicular segment connecting the point and line. Okay, so write it down, think about it, process it a little bit here, because this distance here is going to be shorter than if I were to connect these two and measure that distance here. This might be 7 units in length. This must be further, right? This might be 9 units in length here. What would this be? This would probably be like 4 or 5, right? 5, okay? So the distance between a point and a line is the shortest distance. The perpendicular is actually the shortest segment you can draw from a point to a line. That's called the first minimum theorem, and that'll be that's in the other textbook. They don't actually talk about this one in your 10th grade textbook they're using this year. So the white textbook from the 1950s calls it the first minimum theorem. But anyways, that is distance, okay? So from a point to any other line, how do we get distance? We introduce a perpendicular, okay? So from a point outside of a line, exactly one perpendicular can be drawn, okay? And this would be the distance from point X to line L, for instance, here in this situation, okay? And that's gonna get us to our next theorem, right? A next theorem involving distances from an angle bisector to the sides of an angle, okay? So this is a little confusing. You're like, where is this coming from, okay? So quick reminders here. You just learned 2 theorems. So I want to connect these theorems together. In this section, you've learned about medians, you've learned about altitudes, you've learned about perpendicular bisectors, and you've had 2 theorems about perpendicular bisectors. Now you're going to get 2 kind of related theorems that have to do with angle bisectors, okay? So as a reminder, right, you might be wondering, why is this coming up right now? Because we learn this earlier in the semester, okay? In that every angle has an angle bisector, okay? So we're going to introduce a couple theorems. I know in chapter 1 we talked about angle bisectors. They've been around a while. Perpendicular bisectors just came up. Angle bisectors came up in chapter 1. We're going to come up with some theorems that are going to be very similar to the perpendicular bisector theorem. So you just learned a second ago here. Okay, so check this one out here. Every angle has a bisector, and so maybe I'll sketch this out in the diagram the way they have it written out. Maybe I'll even draw it differently so that you see a different angle experiencing the same thing, the same theorem that you have up top here. Okay, so put this in your notes. If a point lies on the bisector of an angle, does every angle have a bisector? Yes, it does. Let's draw that in. So let's, first of all, let's make this angle ABC. Okay, it's just a generic angle right here that we're going to work with. It's not right. It's, nothing, no crazy tricks, no magic tricks here, no spooking of you guys here. We're just going to do this the honest way, proving way. Okay, so angle ABC. If a point lies on the bisector of an angle, so every angle has exactly one bisector, right? I know that from the protractor postulate, right? Protractor postulate tells me that angle ABC is going to have a measurement between 0 and 180. And if that's a real number, right, real number before 0 and 180, I'm going to be able to divide it by 2. So you can divide any real number by 2. And because of that, I'm going to have exactly one angle bisector. Exactly one angle bisector. Okay, so that's going to be there. So I'm going to draw that. That's how your problem starts here. But if we have a point, okay, if we have a point, I can select any points here. And this here, I'll just remind you guys if you're wondering what this is here. This is, again, the angle bisector. We'll put it on here because you zone in and out of this explanation. Angle bisector, we have a point. So let's just choose this point here to demonstrate this here. Point P, okay, point P. What's a fact we know about point P, okay? Well, it's on the angle bisector, so sure, we're creating congruent angles right here. So that's interesting. You can imagine a lot of like design features of like things opening up like this, and you want to get stuff kind of in between there. We want to say stuff about that. It turns out here, this point P is kind of like point B in that it's equidistant from these 2 rays, right? These 2 rays here. So it says here that point P, if a point lies in the bisector of the angle, then the point is equidistant from the sides of the angle here, okay? So think back to like 5 minutes ago. How do we measure distance, okay? So it looks like PA kind of looks pretty close to PC, but is it really? Is that how you measure distance? No, we don't know for sure if PA equals PC. We have no idea. What we do know, what we're going to prove in a second here, is this distance here, remember, we draw distances by drawing in the one and only perpendicular, okay? So through a point outside of a line, exactly one perpendicular can be drawn, okay? So this is distance, okay? This is from distance from point P to ray BA. This is the distance to ray BA, and it's the distance because why? How did I draw it? I drew a perpendicular segment, okay? So this is the distance here, and that's a shorter distance than going here. That's gonna be a longer segment. This would be a longer segment. Going to PA, that's certainly a longer segment here, okay? So the question is here, is the distance to BA, is it the same as the distance to, just do dis here, to ray CB, or BC, ray BC. Okay, is it the same here? I'm gonna put my question marks on here, and you guessed it, we're gonna prove it real quick. Okay, so let's look at that. Let's use our tricks here, our rules that we've done before, and see if we can get this thing through. So angles, right? Definition of angle bisector, right? This is the P's on the angle bisector. We're just trying to see if it's equidistant. So those angles are the same. Ooh, okay, so we have reflexive as well. You see that? I hope you see that, right? 1, 2, 3, I'll do that here. So we have an angle, we have a side. What else do we have? Ooh, we have another angle. Right, we have another angle. We have another angle over here, okay? So here, if you were to prove this one out, the way you can do this here is that triangle XBP is congruent to triangle BYP by what reason? By what reason? By HL, we have the hypotenuse are congruent. Do we have a leg congruent? No, we're trying to prove that leg's congruent, so we don't know that here. It's not HL, it's AAS, by AAS, okay, by AAS, okay? So that means that PX must be equal to PY by CPCTC, okay? So you have to say that in the proof, but you have to say all the other stuff before that, right? Definition of angle bisector, reflexive property, and here, we've arrived at it that any point that's on the angle bisector, okay, is gonna be equidistant. Right? So we're equidistant to point X and point Y, and that's the foot of the perpendicular, right? From that point to the line here, okay? And we got it good to go, okay? Last theorem for you guys. I got 5 minutes, 5% of juice left here. It's actually the second time I'm filming this. I'm pretty frustrated. My video failed last time. Hopefully this doesn't want to fail again. Okay, so that's something to remember, right? I might put this in your exit ticket. How did you prove those triangles congruent? Or how do we know that those triangles are congruent? Here's another one here. If a point is equidistant from the sides of an angle, then the point lies on the bisector of the angle. Oh, interesting, okay? So here's another one to write down and worth considering here, is that if a point is equidistant, so here, let's do the same thing. Let me just draw it down here. You should be copying down the theorem, right? So that you've written about it, you've thought about it, maybe pausing the video if you need to. That's a long video, but maybe you have to pause it. So let's check it out here. We have X, oops, sorry, this is A here. Let's get the same thing here, triangle ABC. Okay, and this is a random angle. So what we're gonna do is if a point is equidistant from the sides of an angle, then it's gotta lie on that angle bisector. Let's see if that's true. So what is this? This is just the converse, right? The converse of this. This is gonna teach us more about triangles later on this here too. So you do have to know this one here. This is the converse of the previous thing, the previous theorem about angle bisectors here, okay? So if we have a point, let's say this point right here. Let's do a point, we can do a higher, let's do it right here. Okay, that point right here, let's just say that it's equidistant to this side and this side. That means the perpendicular, the one and only perpendicular that I could draw from this point to this side, and the one and only perpendicular I could draw from this point to that side. What if they're congruent to each other? What if those perpendicular segments are congruent to one another? The question is, can we determine that it's on the angle bisector? Okay, so let's see here. Is this going to be the angle bisector? Because the angle bisector would be, right, would go through the vertex and go through P here. So the question is, can we prove that those angles are congruent? Those angles are congruent. And who sees it here? This is where it's easier in class. We're like, who sees it? Who sees it? How can I get that triangle congruent to that triangle? So if I can, then through CPCTC, I would get these two congruent. And then ray BP would be the bisector of angle ABC. Okay, so let's see if we can prove it. Well, we have this by given to us here. Definition of distance is that it's a perpendicular segment. So I have perpendicular here, I have perpendicular here. So I have side, I have an angle, I have an angle. What else do I have? You guessed it, reflexive property right here, okay? And wait a second, is this isn't AAS, right? We only have one angle and one angle. We have side and side, and we have side and side. So here, is this the dreaded ASS? Is this the dreaded ASS correspondence? AA, SS, and SS? Well, if you use ASS in a proof, what are you? Okay, so it's not ASS. Which one is this here? Let me get rid of those things here. You guys remember this here? What special kinds of triangles are these? It's not just that these angles are congruent. What types of angles are they? They're right angles here, okay? So these triangles would be congruent. Okay, so triangle, let's actually put the points down here. Foot of the perpendicular here is X. Foot of the perpendicular here is Y. So we have triangle XBP congruent to triangle YBP by the HL theorem. Okay? Therefore, this symbol stands for therefore, the three dots in triangular form right there. That's actually a time-saving thing you can use for future proofs. Therefore, we know that angle PBX is congruent to angle PBY by CPCTC, and we've proven our proof here that BP ray BP bisects angle ABC, and that's the definition of angle bisector. Angle bisector is the ray that creates two congruent segments out of the larger ray right here. My phone's blowing up here, okay? And I'm fading fast. Like the quality of my videos here is really poor here, okay? So HL theorem right here, I might ask you that in the exit ticket. What proves those triangles congruent? Let's prove those triangles congruent. Anyways, have fun with that one here. All right, so we got it down there. 4 new theorems. Do you have to be masters on those theorems right away? No, you don't. You have an exit ticket now this weekend, and then there's no video lesson on Monday. Thank God for that. You've gotten through all the theorems that you need to know in chapter 3. That's pretty exciting, okay? So now we can start hitting the brakes a little bit here for the rest of the semester. So you had a hard week of work this week. Thank you so much for all your effort. And I think we can end the semester in a pretty good place here now that we've gotten done with this one here. So think about maybe these 4 theorems you've learned today. Ask questions. Think about the definitions of medians and altitudes, perpendicular bisectors, and we'll keep playing with this stuff next semester after we're done practicing it over the next few days. Take care, guys. Have a great night. Have a great weekend. And best of luck in your exit ticket. Please message me if you have any questions.